Chemical engineering is all about turning raw materials into useful, everyday products through chemical processes. The clothes we wear, the food and drink we consume, and the energy we use all depends on chemical engineering. Chemical engineers work out the processes applying the principles of chemistry, biology, physics, and math. They transform raw materials from the environment into desired products, while also helping to manage the world's resources, protecting the environment, and ensure health and safety. The advances of chemical engineering can be found all around us, from innovation and improvements that lead to new medicines, electronic devices, and high-performance materials, to new technologies for cleaning the environment and feeding and clothing the world's people. Chemical reaction engineering is the engineering activity concerned with the exploitation of chemical reactions on a commercial scale. Its goal is the successful design and operation of chemical reactors, and probably more than any other activity, it sets chemical engineering apart as a distinct branch of the engineering profession. Chemical reaction engineering aims at studying and optimizing chemical reactions in order to define the best reactor design. We use knowledge and experience from a variety of areas: thermodynamics, chemical kinetics, fluid mechanics, heat transfer, mass transfer, and economics. Chemical reaction engineering is the synthesis of all of these factors with the aim of properly designing a chemical reactor. The project was to design a reactor to produce 10,000 metric tons per year of maleic-anhydride from butane. A versatile compound, maleic-anhydride is a highly reactive chemical intermediate, being present and having potential uses in practically every field of industrial chemistry. Mostly, maleic anhydride is produced on an industrial scale for applications in coatings and polymers. As a matter of fact, around 50% of the world's maleic anhydride output is used in the manufacture of unsaturated polyester resins, which are further used to reinforce plastics. In 2015, as much as 2,700 kilometric tons of maleic anhydride was produced worldwide, virtually doubling the quantity produced the year before. In order to obtain the desired product, the reactants will pass through a packed bed reactor filled with solid catalyst particles, each about the size of a grain of sand. The decision to use a PBR rather than other types of reactors is driven by advantages such as high conversion per unit mass of catalyst, low operating cost, and continuous operation. On the other hand, PBR has poor temperature control, which we will manage using external cooling, provided by a mixed salt jacket. The heat transfer is a significant issue during the process due to the large exothermicity of the reactions. This is even more of a critical issue since the main competing process is full combustion of butane, a conversion that is twice as exothermic as the partial oxidation. The current commercial process to produce maleic anhydride employs a vanadium phosphorus oxide catalyst to selectively oxidize butane. Butane is fed into a stream of hot air, and the mixture is passed through a catalyst bed at high temperature. The flow of gas makes the catalyst particles behave like fluid. One important aspect for engineers is the ratio of air to hydrocarbon, which must be closely monitored to prevent the mixture from igniting. The main challenges of the project were to calculate the number of reactor tubes and the mass of catalyst required to produce 10,000 metric tons per year.